All right, so for this problem, we have a wave that has a period of 10 seconds. It's in a water depth of 50 feet, and it asks us to solve for the wavelength, single wave celerity C, and then group celerity C sub G for the wave. So again, following the same process as before, we're going to find the deep water wavelength of our wave with gt squared over 2 pi. So that'll be 32.2 feet per second squared times 10 squared all over 2 pi, and that'll give us a deep water wavelength of 512.5 feet. Second, we check what our depth divided by deep water wavelength is going to be. So 50 feet divided by 512.5 feet gives us 0.097. So if we look at our classification table, if our d divided by L naught is less than 0.5 but greater than 0.05, it tells us that we have a transitional wave. All right, and what that pretty much means is the wave started out in deep water, it's eventually going to end up in shallow water, it's going through the transition between the two of them, right? So if we go ahead and look at our equations, we see that for a transitional wave, the wavelength is equal to gt squared over 2 pi times the square root of hyperbolic tangent of 4 pi squared times d all over t squared g. And then I'll finish my square root sign. All right, so that's not great. So a couple things to notice about this. If you've never used hyperbolic tangent before, you do have access to it on like your normal TI-36 calculator. All you have to do is when you see the tangent button, if you hit it once, right, you get tangent parentheses. If you hit it again, you get tangent -1 parentheses, your normal inverse tangent function. If you hit it a third time, it switches to hyperbolic tangent, right? And these hyperbolic functions, these hyperbolic sines and cosines and tangents, there are a bunch of weird combinations of e to the x plus e to the -x, and so we're not going to use them in this class other than simply knowing how to get access to hyperbolic tangent for these specific problems. Now, what you might also notice is that this first part, gt squared over 2 pi, well, that's just equal to the deep water wavelength, which we've already solved. So that's kind of useful. So if we go ahead and plug in values for this, gt squared over 2 pi, we already know that that's 512.5 feet. And then we have our square root sign. And then we have our hyperbolic tangent of 4 pi squared times the depth of 50 feet all over 10 seconds squared times 32.2 feet per second squared. Close the parentheses and close the square root. Now, when you're actually evaluating this on your calculator, I would recommend doing it in steps. I would recommend evaluate this expression, then take the hyperbolic tangent of it, then take the square root of that, and then multiply by 512. Trying to just punch in all of this at once, like you'll probably get it right, but you run a risk of fat fingering on your calculator something and getting it wrong. So anyway, if you plug all of this in correctly in your calculator, you'll get 378.8 feet. Right, so does this make sense? Well, yeah, so we know that waves start out in deep water and they have their deep water wavelength, and as waves move in to shallower water, the wavelength goes down. The waves, the spacing between the waves gets closer together and they slow down. So that makes sense. All right, so next up, we can solve for our single wave celerity, or C. So if we look at our table again, we can see that when we're doing transitional waves, C is just equal to the wavelength divided by the period. Now, it's important to note that's the wavelength, not the deep water wavelength, right? So you have to do the gt squared over 2 pi square root hyperbolic tangent before you can go do the single wave celerity, right? So since we've already done that, it's really easy. 378.8 feet divided by 10 seconds gives us a single wave celerity of 37.9 feet per second. All right, so far so good. So then we get to the most complicated of the three, the group celerity, or C sub g. All right, so for a transitional wave, there's kind of an intermediate step you need to do before you can calculate it. So if you look either on the equation sheet or in the lecture slides for this lesson, you'll see a graph that kind of looks like this, right? Obviously not drawn to scale, right? 0.5, 1, 0.5, and then this is at 0, right? So the way this works is if you have a transitional wave, you can use this graph to figure out the ratio between the group celerity and the single wave celerity, right? So if we go to our graph, we calculated that our d divided by L naught was 0.097. So if we go to that point on the graph, read it up, read it across, again, not drawn very well to scale, you get a value of 0.89. All right, so what does that tell us? That tells us that CG divided by C is equal to 0.89. Therefore, CG is equal to 0.89 times C. And since we already solved for C, it's very easy to plug in 0.89 times 37.9 feet per second and get that the group celerity is 33.7 feet per second. All right, and now if we go ahead and look what's happening, we know that when waves are in deep water, the group celerity is equal to half of the single wave celerity. And we know that when they're in shallow water, the group celerity and the single wave celerity are equal. So looking at this chart, this is how we show that the ratio of group to single wave celerity starts off at 0.5, and then as you get shallower and shallower and shallower, the two values approach the point of being equal to each other, and we say that they are equal to each other at a depth to deep water wavelength ratio of 0.05, which you'll see in the next example.